Who here uses a web browser sometimes? Yeah, so our next speaker works on a web browser called Chrome. He works for Google. And I assume most of you know of JavaScript, it's a programming language. So JavaScript around 2008, 2009 started getting much faster through compiler technology. And our next speaker works sometimes on JavaScript and sometimes on something called WebAssembly. The point of WebAssembly is to allow you to run native code inside your browser and many other things, as he'll tell you. Now, he joined Chrome in 2011, right? So the browsers got way faster around 2009, and then they kind of hit a ceiling with JavaScript. And so what browser vendors started doing is looking at how we could bring more speed and more capabilities to the web through sandboxing technologies and other stuff. That's what Ben has done since 2011. After a few years of doing this, the browser vendors got together, all four of them, formed a standards committee for WebAssembly, and Ben is the chair of that standards committee. So not only is he the implementer of a large part of the toolchain you use when you target WebAssembly, he's also the implementer of what's in your browser and helps guide the technology forward through the standards committee, just like the C++ standards committee guides the implementation of C++. So there's no better person to tell you about WebAssembly than Ben Smith. Ben?
Thanks, John. Wow, this is amazing. Welcome, everyone. Hold on, let me unlock my computer. Yeah, great. Okay. Welcome, yeah. Well, first of all, I want to thank you all for coming. This is such an honor to be here, to be able to speak to all of you. And I also want to thank JF for that great introduction. JF and I worked together for a long time. Since 2012, we were at Google together, worked together for 4 years. And JF has actually been encouraging me to do all sorts of things like this, give talks. But it didn't start with this talk. It actually happened a long time ago. So back in 2016, JF asked me, would you like to give a presentation for the Chrome All Hands? That's where all of us on the Chrome team get together and talk about new technologies, things that we're working on. So I said, sure, why not? It was a great experience. It was nerve-wracking to be talking to my boss's boss's boss, but I did it. Then later that year, JF signed up for a talk, Full Stack Fest, but then decided he didn't want to do it. And he said, oh, Ben, do you want to do it instead? And I said, yeah, okay, why not? I ended up giving the talk in Barcelona. It was amazing. It was a really great place to be, and it was excellent to be able to meet so many people and tell them about WebAssembly. So I've been talking about this for a long time. As JF mentioned, I'm the chair of the WebAssembly community group, and he was the chair before I was. And so when he came to me and said, actually, I don't know if I want to be chair anymore. I want to focus on C++. Do you want to be chair? And I said, okay, sure. So obviously, when JF said, do you want to speak at CPPCon 2019? I said, absolutely not. Okay, so don't get me wrong. Actually, this is amazing. I love C++. I've been programming in it for something like 25 years. But I actually had previous responsibilities that I had to take care of. In particular, I'm currently in a program called Google in Residence. This is a program where we take software engineers from Google and we send them around the United States to historically black colleges and universities or Hispanic serving institutions. And the idea of the program is to try and have better connections between industry, like Google, and education. What we found is that our diversity numbers are not great. We have diversity report, and what we've found from this diversity report is that we need to do a lot better. And this is one way that we are trying to do that. And so what happens is a software engineer is, like me, is embedded into this university, and I teach intro to programming. So this program actually works with 13 schools around the United States. Cal State Fullerton, University of Texas, El Paso, even in Puerto Rico. And so a bunch of my colleagues are currently teaching classes in these locations. So when I applied to the program back in January, I knew that I was going to be accepted. I was pretty sure I was going to be accepted. And so when JF contacted me, I naturally told him I can't do it. I'm going to be too focused on this work. And so when I was accepted, I ended up at Morehouse College, which is this school here. So Morehouse is a school that probably is most famous for being the school that Martin Luther King Jr. Attended. He entered at the age of 15, actually, and in 1944, and he graduated with a Bachelor's of Art in Sociology. School was founded in 1867, and it's actually one of the only remaining men's colleges in the United States. It's located in an area called the Atlanta University Center, where there's a couple of other HBCUs nearby. Spelman, which is a women's college, and then Clark Atlanta University as well. So as I said, I knew that I was going to be incredibly busy. I'm sure some of you are teachers. There's a lot of work that goes into teaching. I've only been teaching for 4 weeks now, and I'm already incredibly overloaded with things like preparing lectures, grading homework, teaching labs, mock interviews, because a lot of these students want to be able to be prepared for coming in and doing an interview at Google. So naturally, I told JF I just can't do it. But if you know JF, you know that he's a very persistent person. And so when he said, he asked me again, I actually thought, oops, let's see, maybe I should try this. Pardon me while I take a sip of water. So it turns out that the languages that are taught by the GIR instructors, my fellow colleagues, is primarily Python. Maybe not super surprising. Morehouse actually is one of the schools that teaches C++. I know it's hard to imagine, but yeah, just one of the 2 schools teaches C++. And so when I told my colleagues about this, they kind of said this to me. Really? C++? Are you going to teach undefined behavior? Are you going to teach them pointers? Are you going to teach them lambdas? Are you going to teach them all this stuff? And I said, no, I'm not going to teach them all that stuff. We're going to teach intro. And so this is one reason why I was a little bit concerned about teaching C++. If y'all have ever tried to use C++, there's a lot of stuff that you need to learn. You have to maybe learn the command line. You maybe have to learn tools like Vim. You might have to learn tools like Git. You might have to try and remember how to quit out of Vim. Right, so then you have to remember how to compile your code. Oh, wait, no, you have to remember to run Clang++, of course, sure. Then, of course, you want to commit your code. Oh, no, you can't just run commit. That doesn't work. You have to add. No, you can't do add. Right, oh, git add. OK, nope, well, I added the executable. That's wrong. OK, so you have to remove that. Right, so I didn't want to have to teach the students this. So it turns out that there's actually a really great tool that a lot of schools are using, and it's called RepLit. And so this is an example of what it kind of looks like. Essentially, on the left-hand side of the screen, you have the code that you can type in. On the right-hand side of the screen, it has a sort of a terminal view. And you can hit the big green button at the top, play, and it'll compile your code, and it'll run it, and then it'll print your output. So you can see here, I have a very, very simple program. This is something that my students could write, and then you can run it, and you can see the output on the right. So I imagine, I don't know exactly how RepLit works, but I imagine it works something like this. you say something like, compile and run my code, and it sends from the client to the server, and then the server says, okay, I compiled it, and I linked it, and now it's running. And then it comes back to the client, and meanwhile, it also says something like, oh, by the way, what's your name? Because the program's now running. And then you send your output across, and then meanwhile, the server's waiting for your response, right? It's just sitting there running your program. And then it returns with the actual result. So this is something like, I mean, if y'all have used Compiler Explorer, this is very, very similar sort of behavior, right? Client-server architecture. But one of the problems is, of course, with client-server programs is like, sometimes the internet doesn't work very well. And it actually turns out that at the university, this is a real problem. Like, we've been sitting in labs before where, the students will raise their hand and say, oh, and I'll come over, okay, you having a problem with the program? And they're like, no, I can't run the code. It's just sitting there loading. And so a lot of the students actually have their own personal hotspots on their phone. And so whenever it goes down, they just sort of pull up their hotspot and they start working. But if they don't have their hotspot, they can't do it at all. So the reason we use REPL.it, I mean, part of the reason was because of not having to learn the terminal and stuff, but part of it is also because these students, they have a wide variety of computers. Some of them work on iPads, some of them work on Chromebooks, some of them work on Macs, and all sorts of different computers. So we need to do something better, I think, maybe. And so I had this thought. What if we take our client code and we say, okay, give me the full tool chain, and then the server says, okay, here you go. And it says, all right, here's all your data, and then you can just do everything client-side. Yeah, why not? And then the server can just sit there and, I don't know, calculate digits of pi or whatever servers do when they have nothing better to do, right? So I wasn't the first person to think of this idea. There's actually a really great project that Todd Fleming have worked on before called Clang in Browser, and it does something very similar to this. I have a little bit of a different implementation, but I wanted to talk about some prior work here. There's also, I can't pronounce his name, Fabrice Bellard, JS Linux, which actually solves this problem by compiling an entire x86 machine inside of the browser. And of course, you can do this. You can run GCC here. I think it takes 15 seconds to compile this, something like that. Because, of course, it's emulating the entire x86 machine to do it. But it does work. So this is a possibility as well. Very, very cool demo, by the way, if you want to check out some stuff you can do in the browser. So the thing that's the common thread about both of these is that they use WebAssembly. As JF said, WebAssembly was designed to do this. It was designed to run this type of code in the browser, things that JavaScript could do, but maybe wasn't well suited to do. Right, so when JF asked me, he said, yes, please, please come to CPPCon, I finally said, all right, let's do it. Honestly, how hard could it be, right? I'm just teaching classes and then also coming up with an awesome demo of a thing that I haven't written yet and producing a 90-minute keynote. So, not so hard. So here's the plan for the talk. First, I'm going to talk about WebAssembly and WASI. I'll tell you what WASI is. Then I'm going to show you how I made the demo. And then finally, I'm going to have a demo time with some live coding, and we'll see how that works out in the end. All right, so first, what is WebAssembly? You probably have seen, if you've heard anything about WebAssembly, many, many articles and talks and podcasts about that actually ask this exact question. So rather than reiterate, I actually took a quick search of the top hits for what is WebAssembly and made a little nice dot graph of all the different words here. So you could probably, I don't know, it's a little bit hard to read, but if you follow through, you can probably find what I think is probably the best definition, which is WebAssembly is an efficient, safe, low-level bytecode for the web, standard binary instruction format for the web. So clearly, that is what WebAssembly is. Okay, not really. WebAssembly is really kind of all of these things. It's about being low level, it's about being a VM, it's about being binary format, but it's a lot more than that. Previously, WebAssembly was actually at CPPCon. So Dan Goman, who still works on WebAssembly at Mozilla, gave a talk in 2016. WebAssembly was still pretty new then. It wasn't yet officially released. I think you could play around with it. And actually, even just last year, Damien Boole gave a talk about WebAssembly and some of the cool things you can do there. So this isn't the first time we've heard about WebAssembly, and probably not the last. I'd like to think. Anyway, both of those talks do a lot of talking about what WebAssembly is, and so rather than repeat what they've said, I'm actually going to try and take a little bit of a different tack. So what I want to do is talk about how WebAssembly is different than the things that you know. Right? Since everybody here uses Compiler Explorer now, you're all experts at assembly language, I'm sure. And so let's talk about how WebAssembly, which we like to think of it as being an ISA, is similar and yet different for some of the examples that you can see here. Okay, so the first thing is that WebAssembly is a typed stack machine. So that means that at every point in time in the program, the type of a stack slot is known. But it's not a pure stack machine. We actually have unlimited virtual registers. So what that means is that you can use locals to access values that you don't want to necessarily store in the stack. So sometimes people say WebAssembly is not a stack machine, but it is. It's just we've got sort of an escape hatch as well. So this just gives you a little bit of an example of the stack machine. If you did something like 1 + 2, you would say I32 const 1, I32 const 2, and then I32 add. So the first instruction pushes the 1, second instruction pushes the 2, and then the third instruction pops those 2 values and then adds them and then pushes that result onto the stack. So we could take a C++ program like this, and we could translate it into WebAssembly, something like this perhaps. So you can see at the bottom, it looks kind of Lispy. That's just sort of a syntax thing. Internally, it's really just storing numbers, values here. So you can see the basic behavior here. One thing to point out is that you don't actually need to return values in WebAssembly. The last value on the stack is the implicit return value. And you can also see an example here of using locals. So local.get is an example of being able to pull that parameter in from the function and then return it thusly. All right, so another thing about WebAssembly is that WebAssembly is validated before execution. A lot of CPUs maybe don't do this, right? But because it's statically typed, we can actually validate the entire binary. And this is necessary, right? One of the things that reasons that we created WebAssembly is because we need to be able to take code, untrusted code from the web, and then run it in the browser, right? So we need to be able to rely on the fact that that code isn't going to be able to do anything nasty. So obviously we can take that code and we can validate it. Some of the other things we do is that we bounce check all memory accesses. So just to make sure that we don't allow you to read outside of the bounds. So just an example of that, if we have our function like this, and then we try and call it with a float value, that's what that F32 const is there, then we actually get a validation error. And what that means is that when you actually try and run the code, it won't actually even run. You won't get to that point. It's basically like you had a compile failure. But it's actually running on the client side when that happens. Another thing about WebAssembly is that it has a machine-verified formal specification. And this is very important, actually, because like C++, we need to make sure that a lot of different people can use WebAssembly and can implement it, right? So, for example, Chrome has an implementation of WebAssembly, and so does Firefox, and so does Safari WebKit, and so does Edge, and so does a lot of other implementations that are not even browser-based. So having a formal specification actually means that everybody can be fairly certain that their code will run the same in all those different environments. So here's some papers. There are actually some really great stuff in here. The first one is the sort of original WebAssembly paper, bringing the web up to speed with WebAssembly. There are a number of authors here. And it's actually a really great read. It's like 15 pages, and you can, I think it's 15 pages, something like that. And it goes through a lot of the important details of WebAssembly. The second paper here is mechanizing and verifying the WebAssembly specification. So this is where researcher Conrad Watt actually did a machine verified the implementation using Isabelle. And then the last one here is actually the core specification. We're a W3 standard, and so it's currently a candidate recommendation. Actually, I think it's currently a proposed recommendation. I think it just happened a week ago. And you can read through the spec here. It's, I've heard people say that it's difficult to read, but if you can read the C++ spec, I think you could probably read this. And it goes into actually a lot of really great detail about how everything works, even floating point. So like, if you've tried to read the IEEE 754 spec, you might find that it doesn't go into a lot of mathematical detail, but this spec actually does about all the operations that we do. So it's pretty cool. Another very, very cool thing about that first paper, at least I think it's cool, is that these two, I guess, pages here have the entire typing semantics and the entire execution semantics on one page. So you can just sort of look through, and I mean, it's hard to see here. I guess I should have had a higher resolution, but it's very cool to be able to just sort of like scan through and see the entire behavior of WebAssembly on 2 pages. Okay, so another thing about WebAssembly is that it's a Harvard architecture. So this means that the program state is actually separate from its code, right? So it's not very common in most systems, but it actually does provide some benefits. It actually means that it's impossible for a program to read or write anything in its instructions. It's not possible to modify the call stack. So that might look something like this. So the top part would be, say, your trusted code. You might have things like the binary format of your WebAssembly blob. You might have some internal data structures. You'll probably have your compiled x86 code, and then the actual call stack. And then at the bottom, you'll see something which is our untrusted memory. And that's the only memory that WebAssembly can actually access. It can't access any of the stuff on the top. And this does prevent a certain class of exploits. So for example, like return-oriented programming isn't possible with code like this because you can't modify the stack. So another example, and this is probably the most controversial thing, is that WebAssembly has structured control flow. What that means is that we don't have a go-to statement. We don't have a go-to instruction in WebAssembly. Instead, what we have is very much like you might expect in a very low-level programming language. So we have a thing like a block, and what a block means is that when you branch to a block, it branches out to the bottom of it. We have a loop, which means when you branch to it, it branches to the top of it. And you can also have structures like if, which allow you to branch outside of it. So if is sort of a syntactic sugar. You don't need it, but it does make the code a little bit smaller, which is important when you want to send it over the web. So here's an example, the obligatory compiler explorer example. One cool thing about this is that you can actually produce WebAssembly code in Compiler Explorer by passing --target equals WASM32. I think there was actually a dropdown for it for WebAssembly that my colleague added, and then maybe it was removed. I don't know. Yeah, not on purpose. Not on purpose. Okay. Yeah. So it was there before, and maybe it is there now again. I'm not certain. But so this is an example of some code here, and so I'm going to try and recreate it here, so we can look at something a little bit more interesting. So this is what Clang did with an example where we're basically just doing a search through a linked list. So you can first see that Clang already did a nice unrolling of our recursive function. And I'm going to try and get into some of the detail here. So the first thing you can see is we actually turn that recursive call into a loop back to the top. So you can see that BRF at the bottom there. BRF is a conditional branch instruction, and allows you to decide whether or not it takes the value on the top of the stack, compares that to 0. If it's non-zero, then it branches to the top. Then you can see this BRF at the top. That BRF is essentially doing the equivalent of this if not root, then return root. And you can see actually something cool here. We branch to the bottom and we just return 0. And we know, of course, that root must be null in this case. And so we don't actually have to read it again. We can just return i32 const 0, which is our null pointer. Yeah, okay. So here's the next section here where we actually do a comparison. Let's drill into that a little bit. So the first part here is where we actually say, take the root's x member and then compare it to x. So you can see here we do local.get0, and then we do an i32 load that actually reads from that value. Then we do local get 1. Again, that's the value we're looking for. And then we do i32 and e. That means compare if the two values are not equal. And then we follow that up with a BRF that allows us to check whether or not those are true. If so, and actually, yeah, so it actually flipped the check, right? It was an equality check, but the compiler decided it was better to do it as a not equal check. And then it can branch out from there. And then finally, like I said, yeah, we have this recursive call here. Local.get and then i32 load 4 is actually reading the next pointer. You can see because ints are 4 bytes. That's because WebAssembly is a 32-bit machine. And then we have something a little bit weird here. That's the local.t. Local.t is an instruction that allows you to set a value in a local and then also leave it on the stack. So it's just a nice way to be able to use the stack more efficiently, but also set a local value. Okay, so this is a question that I often hear from people when they first hear about WebAssembly. People say stuff like, can WebAssembly render graphics? Can WebAssembly access the DOM? Things like that. Can WebAssembly tuck me in at night? And these are understandable questions because for JavaScript, the answer to a lot of these things is true. Maybe not tucking you in, but a lot of the other things, right? And so the way that I've actually started to answer this question is this. WebAssembly can't do anything. You can quote me on this. Okay, so this is kind of a joke, but like some of the best jokes, it's actually also kind of true. The thing is, WebAssembly can't do anything unless you allow it to. And so the way that works is that you have a WebAssembly module, and a WebAssembly module has a collection of imports and a collection of exports. And so the imports are what your WebAssembly program is allowed to do. And the exports is basically what the WebAssembly module is allowing you to do to it. That's maybe a way to think of it. So for example, if you have a WebAssembly module that has maybe a carnivorous plant living outside of it, you don't actually have to worry about that carnivorous plant being fed unless you provide a feed plant's blood import. If all you have is water plant, then you're safe. So you can actually rely on this. By the way, yes, don't feed the plants. Audrey too, anyone? Okay. So this actually presents a strength and a weakness of WebAssembly, right? Because what we've ended up with is that WebAssembly can't really do anything by default. And what that means is that you can craft a WebAssembly module to do exactly what you want, right? You can provide exactly the imports you want and exactly the exports that you want. But that also means that if you have a web module and a non-web module, you might actually need to provide different implementations. So for example, here we have console log, which is how you might do it if you are using a web module. and you might have a function like write if you're using a non-web module, right? And so theoretically, these modules should be able to run identically, right? There's no reason that we need to actually have a difference here, but there's just no standard. One way you could work around this is by providing a shim. You could have a function that, say, implements these equivalently, but what's better is to have some kind of standard. And that's actually what WASI is. So WASI is also being developed as a standard in the W3 as a subgroup of the WebAssembly group. It was originally proposed by Dan Goman, but there's a large group of people working on this. And the way to think of it is that it's got kind of a similar functionality to a stripped-down POSIX. The difference is that it's actually been developed as a capability system. So unlike POSIX, you know that and similar to WebAssembly, you only have the behavior that you allow, right? So you can't access any files in the file system that aren't actually given to the WASI interface. So currently, WASI is actually very small. There's only 45 functions. If you know POSIX, I think there's something like 300 or 400, maybe, syscalls. You can think of it as being very similar to syscalls. And so you can see some of the common functionality that you'd expect, right? So we have things like being able to read arguments, get clocks. We can read from the environment. We can read a lot of things from files and write to files. We can look up things in a path. We can exit. That's always important to do. We can get random numbers. And then there's some scheduling as well. So the way to think of this is that WASI actually also comes with libc. So when you use it, you can actually write code like fopen, and that will be translated into the WASI function pathopen. Similarly, something like printf will be turned into fdwrite, fread will be turned into fdread, and so on. And since this is, of course, a C++ talk, you could do the same thing with the C++ equivalents. I assume people use fstream. So there is additionally a tool called WASMtime. And one of the things that's very cool about once we have WASI is we can take our environments, web and non-web, and we can run them identically, right? And so WASMtime is a tool that allows you to run WebAssembly code natively in a non-web environment using a different WebAssembly JIT. It's actually called the CraneLift JIT, also being worked on by a number of people at Mozilla. So I just want to give a warning. WASI is still very, very early. I'm going to be talking about WASI for the rest of the talk, but if you try and use this, I just want you to know that there's a good chance that you might have to spend a long time fixing issues, maybe even up to 250,000 minutes. Okay, just kidding. If you want something more mature, there is a much more mature tool chain called Emscripten. It's been around for a very long time, since 2010, I think. Originally developed by Alon Zakai, but now there's a large community of people working on it. It provides a lot of the functionality that you might want a POSIX environment, but it also has graphics, and it has audio, and it has built-in SDL, and it has a lot of features. So if you want a more mature environment, this is what you should use, but this is not what I'm going to talk about today. Just one more thing about Emscripten. This was actually presented at CPPCon as well. So Alon Zakai talked about it back in 2014. And actually, Chad Austin did as well back in 2014, presented on it. Back then, they were using it to produce ASM.js, which is kind of like a precursor to WebAssembly. But a lot of the things from this talk, from these talks, is still true, and you can still use it. So you should go back and watch those talks if you're curious about this. And of course, there's many, many resources online to find a lot more about how Emscripten works. Okay, so the to-do list for now. this is what I basically came to when I wanted to make my demo. I said, okay, well, the first thing I got to do is get an SDK. Then I'm going to compile Clang, and then I'm going to compile LLD, the linker, and then I'm going to be done, right? Okay, simple. This is, of course, after I did nothing. So the plan here is to take the SDK tools, which, by the way, run on x86, but then target WASM32, and then take the LLVM source, and then compile those, and then I will get something which is Clang running on WebAssembly, the WASM32 host, and a WASM32 target. So Clang already is a cross-compiler, but now I'm going to have essentially a cross-compiler based on the, well, I guess I'll have a native compiler for the WebAssembly target. So the first thing I did was I downloaded that SDK from this website here. And the next thing I did was I cloned LLVM from this here. I think it's actually pretty recent that you can actually get LLVM via Git. I think before you had to get it on SVN. So this is very cool. And then I perused these docs here, how to cross-compile LLVM. Very, very useful for this sort of thing. So the first step that you find if you look at those docs is that you actually need the system Clang and the system LD to produce a couple of these files. In particular, there's a executable called TableGen, which is used to actually be able to do the compilation. Normally, when you're doing a compilation of LLVM, it'll do this for you automatically, but when you're cross-compiling, what'll happen is it'll compile for the wrong target, right? And so if you're compiling for WASM32 and then you're trying to run it, then your compiler can't do it. So you do this as a pre-step. You compile it, and then you produce these outputs, which run on x86. So now that I have the tools, and I have TableGen, and I have the LLVM source, now I can take these files and I compile them, and I can do my cross-compile. So when I did that, I got this issue. Atomic is not supported on this single-threaded system. Now, this is a reasonable thing for the WebAssembly SDK to do, because actually threads are currently being developed as a proposal, but they're not ready yet in all environments. And so to be conservative, it makes sense to disable it. I want to say, though, that this is not the long-term goal. We definitely are working on thread support. It's just not there yet. But I knew, for example, that LLVM didn't need threads. Clang and LOD don't need threads, so I was able to just disable the code. So the way that I did that was, it's actually very cool. If you have libc++, they allow you to provide your own threading library, and so I did a very, very nasty thing, which is have them all do exactly nothing. And you'll be surprised, but this actually does work. I see some shocked faces in the audience. Okay, so then I started running into some of the issues that you might expect to see when you're compiling code for a different environment. So WASI doesn't have signals. WebAssembly doesn't either. I knew that I didn't really need any of these, so I basically commented out any of the code that used this. Again, Emscripten, I think, does have implementations of a lot of these. But again, for my case, I knew that I didn't need to handle any of these. Similarly, WebAssembly doesn't have mmap, unmap, and mprotect. We definitely want to support these, but WebAssembly is still very early. It turns out that in my case, I actually knew that I didn't really need the sort of advanced features of mmap, so I could turn this into malloc and free, and that was basically enough to do what I needed to do. LLD actually does have an optimization where they mmap files, and then they can just write directly into it to make it run very fast. It's very cool, though. Actually, they have a fallback where if mmap isn't supported, it'll just write it into a buffer and then write it out as a file. So turns out that they kind of already solved the problem for me. So there's some issues with things like, I mean, by the way, I just want to say, these names are horrible, right? Anyway, so yeah, so these are like things about users and passwords and such. I knew that I didn't need any of this stuff. So again, I just sort of put in dummy values. I forget what I actually put in for these, but I'm sure it was something fun. These ones are a little bit more surprising to me, actually. I think WASI is actually kind of conservative in the features that it provides. And so, in particular, getCWD and RealPath really should be provided, and maybe Tritter as well. And so I basically just wrote sort of simple implementations of those. StatVFS and fStatVFS, those are like basically looking at information inside the file system. Those are dummy values as well. And then DUP2, I think that's actually a capability restriction. But again, I don't think that one was actually required. So I commented that out. And of course, ioctl is the grab bag of the POSIX functions. I think in this case, it was just used to, maybe it was to change the, I actually can't remember. I think it might have had something to do with like changing the width of the terminal. In any case, it wasn't necessary. Okay, so these ones are people's favorites as well, set jump, long jump. Those ones actually are supported in Emscripten in a very, very nasty way. What actually happens is when you call set jump, what actually happens is it calls out to JavaScript, creates a try block, calls back into your WebAssembly, calls your functions, and then when you do a long jump, it actually calls out to JavaScript, throws, and then it catches in the JavaScript block and then goes back. And it turns out that that actually does work. But it's not preferred. And so I will also like to say that there is a proposal, an ongoing proposal to add real zero or low cost exceptions to WebAssembly. That's actually pretty far along. It has some implementation in some browsers. It's a little too early for WASI, and so again, because of being conservative, it's not here. Yes, and then get host name, again, that can just be stubbed out. And then finally, everyone's favorite, the lovely process functions. So things like POSIX spawn and getPid and getSid and waitPid, all that stuff. Yeah, that's more stuff that only is necessary if you run the compiler as a driver. So it turns out because the compiler actually has the compiler and the driver in the same executable, we can just sort of skip all of the process stuff. There are ways we could make this sort of thing work using the host as kind of an environment, maybe running JavaScript as a pseudo kernel. I know that sounds horrible, but you could do it. But for now, I know we don't need these, and so I skipped these as well. Okay, so 28 functions later, I finally had enough to make this work. And actually, in the case of LVM, I only had to touch 12 files because they actually condensed all of the code that I need to change down to about 12 files. It's all in this support library. So it was very convenient to do. So at this point, I started getting some weird link errors, stuff like this, which I mean, I don't know if you can read this, but I certainly couldn't. I asked my colleague Sam about it, and he told me that the problem was actually probably that the libraries that were being generated weren't being indexed. I don't know if anyone's run into this problem before. It turns out that brandlib normally does this. Basically takes your library file and then it puts a little index in there so it can find the symbols more quickly. The problem was that I was using the system's brandlib to try and work on a WebAssembly library, and so as a result, it wouldn't work. So of course, now I have to add another step. I have to compile a LLVM AR and LLVM brandlib for x86, and then use those as well. along with my hacked LLVM source, and actually it doesn't say it here, but my hacked WASI SDK tools. And then finally, I got this all to work. I got a Clang and I got an LLD. So this is what I ended up with. A Clang binary that was about 50 megabytes. I think that could actually be shrunk down. Currently, the one I have is about 35 megabytes after I did I ran an optimizer on it. I think that could probably be smaller than that, though. And then LLD is also 28 megabytes. And so you can see, because we're using WASI, it's not even using actually all of those 45 functions. It's only using about 25 of them. And then it only actually exports one function, start. And the start function is basically the intro, and then we'll call your main function and then run and then do everything. It also exports as a couple of other useful things. You can see that it exports heap base and data end, and then an object called memory. And I'll talk about those now. So the way that WebAssembly memory is laid out in LLVM, at least LLVM-produced WebAssembly, is something like this. We have a giant block of memory. The part at the bottom is unused. It turns out that WebAssembly, a null pointer, is completely fine to read and write because it's just reading index 0 of your memory. So it's maybe a good idea to leave a little bit of space there in case people start scribbling over the null pointer. You don't actually write over any of your static data. So then we start writing our static data at about 1K. We have data end, which represents the end of the stack. And then we have heap base, which represents the start of your heap. And you can see the stack grows downward, like all proper stacks do, and the heap grows upward. And the nice part here is that memory can actually grow. So we can grow the size of the WebAssembly memory, and then the heap will be allowed to expand out in that direction as well. So you might have remembered that I said that WebAssembly doesn't allow you to access the stack. And it turns out that it doesn't, but because we can do things like take address taken local variables or have dynamically sized local variables, we do actually need to have a shadow stack, is what we call it. And this does live in memory. This lives in WebAssembly memory, and you're allowed to access it. So these are a couple of cases where we actually do have a stack pointer that does move inside the WebAssembly memory, and we store it for these values. But only for the values that the compiler knows it needs to actually allocate space on the untrusted stack for. So as I said before, Clang actually is a driver and a compiler. So when you run Clang normally, what happens is it runs both of these pieces for you. So for example, if you do foo.c-out foo, it will compile to a foo executable by running the compiler and the linker for you. And if you run dash hash hash hash, I think that's how you might say that, it will tell you what it's actually running under the hood. This is sort of stripped down version of it, but it gives you the right idea. It runs a number of different arguments here, passing the triple that's required. You can see it does emit obj. That's what the dash O turns. Oh, actually, yeah. That's how that would be the equivalent of like dash C. Yeah, right. Thank you. And then it also passes in things like the sysroot and so on. So one cool thing that we can do now that we have these WASM binaries in WASI is we can take WASMtime, our non-web tool, and we can run our compiler using WASM, but in the just like from the command line. And the way you do that is you run WASMtime, and then as I said, it's a capability system, so you actually have to tell it what it's allowed to access. And so in this case, we say you're allowed to access the current working directory. I'm calling PWD here, and it's called source inside the system. And then similarly, we can access a directory called sysroot, and that's called sys inside the system. So you can see the sort of colors map up here. And so we can run this and test this, and it works. And that's very cool because now I don't even have to, like, there's no JavaScript yet. This is all just running on the command line. And so one cool thing about this capability system is that actually you are prevented, I guess you might say, from accessing outside of there. So in this case, I'm trying to access outside of the source directory. But as far as WASM is concerned, as far as WASI is concerned, that's not a real thing. There's nothing outside of that. It's kind of like you're in a chroot. Yeah, exactly. Thank you for anyone who's helping me out when I'm trying to remember words, by the way. So yeah, this actually uses libpreopen to handle this behavior. I think or it borrows some of the code from that. So this is very, very cool for being able to do sandboxing. Okay, so what we have now is we have WASM, which has the WASI imports already implemented, and then we can use those to run Clang. But if we want to run this in the browser, we actually need to provide our own WASI implementation, because that's not currently provided in the browser yet. It might be in the future, but for now, it isn't. But fortunately, we can write some amount of WebAssembly and JavaScript to be able to implement those imports and then run Clang. So it turns out that WASI actually already has a polyfill for this. But because my job was not hard enough as it is, I decided to write my own in-memory file system to be able to implement WASI here so that I could run Clang in the browser. So this is how I did that. I have my JavaScript code here, and then I have a memfs WebAssembly module that I compiled using C++ and using WASI, which implements the imports that are required for Clang, including things like fdread, fdseek, and so on, as you can see here. And then I have other implementations that are not related to the file system that are implemented in JavaScript. So things like being able to get the arguments from the caller, also being able to read the environment, and things like doing a process exit, something like that. So to make this work, we actually need to add a little bit of functionality that in JavaScript. What happens is we have an in-memory file system that has its own memory, and then we have Clang, which has its own memory. And we want to be able to copy data back and forth between the two, right? Because what will happen is Clang will say something like, read this file, and it has some buffer that it wants to get filled in. And the memfs has that data available, and it wants to be able to take the data from the memory FS and then copy it into Clang. And now currently, WebAssembly does not allow multiple accesses to memory. So a particular WebAssembly module can only access its own memory. But JavaScript has access to both memories. So what you can do is import a copy in and copy out function from JavaScript, which knows how to do the behavior, and then call that from inside memfs to be able to say, copy my data in or copy my data out to the running executable. So the other thing that you need for a compiler, I did not have in my to-do list, is you need includes, you need libraries, and things like that. But one of the very, very cool things about what we just did is that we already have this stuff available in the WebAssembly, the WASI SDK. It needs that to be able to run WASM32 in the first place. So we can actually take the exact same sysroot from the WASI SDK, and we can tar it up together and include that instead, and write that directly into our in-memory file system. So what I did was well, I got ahead of myself here a little bit. I tarred up this data, and I produced a sysroot.tar, and then I wrote a little function in JavaScript that allows you to untar it. And it turns out that actually tar is an incredibly simple format, so I think this function is something like 15 lines or something to be able to read it out into the in-memory file system. It's very cool. And so this actually allows us to do pretty much everything we need. The only other thing I had to add here is that it's nice to be able to, rather than using the low-level interface for reading and writing files to the memory file system, I have a little sort of cheat function that allows me to just write whole files in directly. Just a nice little convenience there. Okay. So taking a step back, this is how our system is set up. We have JavaScript and we have our memory FS. So the very first thing we do is we take our sysroot tar and we untar that into the memory FS. Then the next thing we do is we take our CC file that's in JavaScript somewhere, and then we write that across into our memory FS as well. So now it's available to be accessed by Clang. Then we take that file and we write it into Clang using our copy in when we get a compile call from JavaScript. What Clang will do then is it will use that memory FS and then write it back out as an object file into the same in-memory file system. Then, as you might expect, when you do your link call, it'll take that object file, link it, and then it'll produce a WebAssembly file, again, in the in-memory file system. And then finally, what we can do is we can pull that WebAssembly file out, and then we can compile that using the normal WebAssembly compilation tools, which will produce a new foo module here, which we can then run and hook up to the same in-memory file system. And then it can actually do any of the access that we need to do here. So that gives you maybe sort of a lay of the land here. But I actually was being a little bit, I didn't go into all the details that are required here. So there are a couple of steps that are necessary to produce a WebAssembly module. The module isn't actually the thing that you run. The module is more sort of like the compiled code, you might say. The instance is more like the running process. So the module is sort of like the static data, and the instance is sort of the dynamic data. It actually has the memory objects and so on. And one of the cool things here is that you can actually take a single module and you can produce multiple instances in exactly the same way that you have one executable and you have multiple running processes of that. And so what this means is that we can actually compile our code once for Clang and instantiate it, which is to say, sort of run that process many, many times. And so the compilation is relatively slow, 3 seconds or so, depends on the implementation. But instantiation is much, much faster because all that work is pretty much done. You just sort of have to fill in the holes. There's certain stubs that are not completely filled in, and so instantiation sort of fills in those pockets. Some final things about the implementation here. So there are a couple things that you need to do when you're running on the web. There is a kind of issue, which is that pretty much everything runs on the main thread, including the UI and JavaScript. So if you run code in JavaScript and it blocks the UI, that means your web page won't be able to be interacted with anymore. And of course, the one solution to that is to create a worker. So what I do is I actually create a worker, and that's where all of that behavior that I talked about before actually happens. So when you click a button to run, it says run on the worker, and then it actually runs all of that code inside the worker, and then it sends the results back to the main thread for display. And similarly, I have a service worker that I run. A service worker is kind of like a programmable network proxy. And the idea there is that now when we do a fetch for the Clang module and for the LLD module, they're both pretty large, we can actually cache those on your system. And so the demo that I'll show you very soon actually does that. And it means that once you download it, you don't really have to download it again. So that's pretty cool too. There are a couple of other things that I use, mostly because I saw that Compiler Explorer used them. I don't think Compiler Explorer uses Ace, maybe Monaco. Monaco, yeah, okay. So I ended up using Ace. I also use Golden Layout, which is an amazing tool, very, very cool. Highly recommend. And then I also use Xterm JS. That's basically a terminal that allows you to display all the nice output. I think it's very commonly used. So yeah, these are all really excellent tools and made my job a lot easier for making this stuff look good. All right, and with that, who's ready for some super live demos? Okay. Ah, nervousness. Okay. Can we see this? Can I see this? All right, so this is currently what I have. So this is the first tool that I sort of played around with. This is basically doing what Compiler Explorer does. So I have my terminal over here. Let's see if I can, this is much harder to do than I thought it was gonna be. Okay, so you can see the assembly code on the right. I actually cross-compiled the tool. So I sort of lied when I said that the WebAssembly tool was compiling to WebAssembly. Because Clang is a cross-compiler, you can just add another target in. So I added an x86 as well, so you can see that here. So if I do something like change this to a 2, you can see that it changes that 2 there on the movie AX2 or so on, right? So let's see if I can do the thing that I was practicing. We can do like and do that, and then say this, and it's compiling stuff. And I can say if, let's see, n is less than 2, return b. That's right, right? Then I can do something like this, and this should be b and a plus b, right? Okay. Right? Is that correct? All right, I don't know if it's correct. But what we can do is we can do a test function here. Actually, we don't need that. And then, whoops, we can say return fib of 2. Okay, and we can just increase the sum. Right? Okay, I mean, I think that's right. Okay, so this is sort of like the in-browser equivalent of Compiler Explorer. And yeah, so this is all, there's no servers involved here. I actually slowed down the compiling, but previously I was testing it with compiling like every 100 milliseconds or something. I debounced it, and it was still fine. It's pretty fast. In fact, I have a little show timing here. I think that'll work. We'll see. Yeah, this is way harder to see than I thought it would be. All right, I'm not going to mess with that. I can't find the scroll bar. Okay, so let's look at some other demos. So the cool thing about that previous demo is that it's compiling and it's just producing assembly output, right? But we can also run. Remember, that was what that foo wasm was doing. So we can take our code and we can compile. So you can see this is actually compiling Clang, and then it's compiling LLD, and then it runs. Right? So of course we can, whoops. Oh yeah, I really need a. And so you can see the second time it's a little bit faster. Okay, so clearly my scroll bar is not moving with me, but you can see there. Okay. I'm gonna actually close this and reopen it. Okay. I actually also added some local storage here, so you can see that it keeps this again, just sort of a nice Compiler Explorer feature. So you can see this stuff there. Okay, so let's see. Oh my goodness. Okay, so here's an example. I dropped in the compile time regular expression header. So I just sort of put it in include. So yeah, I'm sure it's fine. And so you can see here, if I compile it, should all compile and work. Okay, so this doesn't actually do anything because all it's doing is the static assert down here. But you can see that it actually does work. So if I change this to like, 2017, yeah, so it gives me an error here. Static assert failed. And you can see it's actually pretty fast, right? I mean, I don't know, this isn't doing a whole lot of work, but I think it's pretty cool that it's like, pretty zippy. Okay, so that's compile time regular expressions. Okay, so here's some silly stuff that I was playing around with. So you can see some lambdas here and things like that. Okay, that's too big. Actually, I can just change it. Let's change that to be a little smaller. So I added some stuff where you can draw a tree and draw a diamond and yeah, ASCII art, right? It's cool. Kids are into it. Actually, the kids are into it. I asked them to do an assignment where they drew stuff with ASCII art, and they had a lot of fun doing that. Yeah, so anyway, just a silly little thing that I wrote up. Okay, so that's shapes. Let's see. All right, of course we need to do our Mandelbrot fractals. Okay, so that's, let's see if I can make that a little smaller. There you go. Yeah, so there's an ASCII art. So that's pretty cool. You can, zoom in and stuff. That's probably not a great place to zoom in, but you can see. So it's not super fast, but I think it's fast enough. Okay. But of course, ASCII art is like not the only thing you can do. So I took small PT, which is a small path tracer by Kevin Beeson, and I made some tweaks to it, and of course added a canvas. And let's see. So actually, I'll leave it here for now so we can see it running. So it's running. You can see it's at like, wait for it. Okay, so it says it's done. Let's see what we got. Yeah. So that's pretty cool. So what's cool about this actually is that it's using the browser's canvas to do this. I basically just wired up imports so that you get all the features of the JavaScript canvas, but you can access it via C++. So you can take a look at the code down here. I made this like little canvas class and then an image data, and then you can write in the data and then do commit. Commit basically takes that data and then copies it out into JavaScript, and then you can do put image data, which is exactly the same name as it is in JavaScript, and draw it. All right, so that's an example. Oh yeah, so then here's an example of something that I actually ported. I originally wrote this in raw WebAssembly, but then I decided, well, why not port this to C++ for the talk? So this is a metaball. So let's see if this works. Yeah, there we go. So this actually does something a little bit sneaky, I guess I'll say, is that there's actually a setup function and a loop function. The setup function is called from main, and then main exits. And then loop is called intermittently to update the frame. And the way that works is actually, I actually throw an exception so that it doesn't clean up any of the data so that I can still access everything after. So that's a super nasty hack, and there will be a better solution for this in the future. But for now, I realized this in my hotel like yesterday that I was like, wait, this doesn't actually work. So I had to like fix that. But anyway, so that's a fun little demo, old school metaball demo. Okay, and then here's everyone's favorite, the Doom fire effect. I basically got the code from Fabien Senglar's book. Excellent book, by the way. And you can actually see that the code, it creates such a good effect. And the code is really simple. You can see it's just like, this is the entire loop that does it. And because this is CPPCon, I'm using the C++ random functions. I copied those from CPP reference because I do not know how to write it otherwise. Okay, last one that I wanted to try and do, I wanted to try and work with you all. Okay, so this is my little starter code that I wanted to start with. It's just doing something simple right now. It takes the image data, it draws a little pattern here, it puts it out, and then you can see the code here, or at least I hope you can see it. You can change the fill style, and you can change the font, and you can change the text here, and then it's actually centering the text. Okay, so if I get rid of this, really should have practiced this. Okay, I can change this to CPPCon, and I should see that, and I can do something like, how does this work? Set fill style to black, and I can do fill rect with height, I think. Okay, that works. And then I can make a little function like draw, and I can take that here. I don't want to center it anymore, so let's do that. And I think I can do this. This is great. Like, I'm sure that all of you are like looking like he forgot a semicolon. Okay, so I think this is looking okay, yeah. Let's make that a little bit smaller. Cool. And now we can do other nasty things like this. Global variables. And we'll just do something like that. And we'll start this off here. This is way harder than I thought it was going to be. Okay, so that's not doing anything yet, but of course I can do, actually, let's make these doubles. I still have time. Is that a plus? Oh my gosh. Okay, so we should be able to run that and see. Okay, it's starting to move. Okay, and of course we want to multiply this by our elapsed. I think that might be too slow. Yeah. So let's do that. It's a little faster. Okay, that's better. And we can say if x is greater than width minus, I don't know. Or x is less than 0, then we'll just turn it around. Why did I decide to do this? I hope y'all are still enjoying this. Because right at this point, I'm just coding. I don't know. Okay. It's got to be faster than this. We can't wait. Yeah. So the problem is I don't know if this is actually going to be able to hit a corner, which is, I know what we all want. Anyway. Okay, yeah, so so that was fun. Okay, did I have anything else that I was going to do? I don't think so. Okay, back to the slides. Back to the slides. Thank you. Thank you for indulging me. Okay. Yes, almost out of time. Okay. Does my clicker still work? No, that's fine. Does anything still work? Yes, okay. So technical limitations of this prototype. First off, reading input, blocking calls, coroutines. Okay, so one of the problems with running on the web is that the web doesn't want to block, right? Everything is asynchronous. And so if you try and do something like cin or reading from the network or anything like that where you need to block, it's just not going to work. There is a way to do this by transforming your code. Alon Zakai, the author of Emscripten, actually added a feature called a syncify, I think it's called. And he gave a talk about it, I think 2 days ago, actually, where he goes into details about how you can convert code that does do blocking into sort of like maintaining and sort of unwinding and rewinding the stack. So that's a good tool-based solution, but there's also, in the future, we're gonna have solutions for this using the exception handling proposal to provide something like delimited continuations. So watch this space for that feature. Exceptions. As I mentioned before, exceptions are not currently supported. I think if you tried to throw an exception, it would just abort. But this is, again, a proposal for WebAssembly. We're actively working on it. We're going to add this feature, I hope, very, very soon. Threads and atomics. I mentioned this before, but it's just not currently in the tool. We're working on it. There's a proposal. I'm actually the champion of the proposal, and I'd really like to see it move forward. We have an implementation in Chrome, but the spec is a little bit further behind. So. Just some quick links. If you're interested in WebAssembly and you want to come to the meetings, they are open. It's a WebAssembly community group. You can go to meetings and you can see all the notes from our previous meetings. If you're curious about the future proposals, go to WebAssembly proposals. There's a huge list of them, the champions and their current stages. If you want to read the spec, there's this link here. If you're interested in WASI, go to WASI Dev. Of course, emscripten.org. And then this demo that I just showed you is right there at Binji GitHub IO WASM Clang. Yeah, it's very alpha, so, you know, do it with what you will. And that's it. Thank you. I have 11 minutes, so if people have questions, I have answers or I have dodges.
Hi, thanks for the talk.
Thank you.
At the very end, you mentioned that exceptions are not supported, and by that you mean that exceptions in WebAssembly are not supported, or their exception in the compiler which targets, the C++ compiler which targets WebAssembly are not supported, or both?
Yeah, so the question is, I said that exceptions are not supported. What did I mean? And the answer is yes. So obviously, exceptions are supported in Clang. You can use them. They will be compiled, but they will be compiled into an abort currently in my implementation of this. In the future, there's active work adding exception support to LLVM. I think it's pretty much there, but don't quote me on that. And at that point, you should be able to use it to compile to WebAssembly using the new exceptions proposal, and then be able to run that in WebAssembly as well. Does that answer your question?
So if I compile code with exceptions, C++ code that uses exceptions, will it run or will it abort?
It'll run, but it'll abort if you throw currently.
If I throw
yes, but in the future,
it will be supported. Right.
And if you use Emscripten, it actually, like I says, turns exceptions into a thunk out and a thunk back. And so that actually will work. But that's sort of a stopgap until we actually have the full support.
Okay, right, thanks.
Thank you.
Hi, Ben. You mentioned this workaround, I guess, for the fact that in WebAssembly you can't share memory between different modules. So you kind of go back to JavaScript and have it. So are there plans to loosen that limitation so it doesn't feel so hacky?
Yeah, there are plans to reduce that. It's actually, the binary format is extensible to this point where we could actually add support for multiple memories. We currently just have a limitation. There's no current proposal about adding multiple memories, but we've talked about it a lot for exactly this reason. Yeah.
So in this slide of yours with the memory map, I don't see a code section. So how do function pointers work? And also, how do
yes.
C++ member function pointers work?
Yeah, so the question is, how do function pointers work? Yeah, I kind of glossed over that entirely. They do work. There's a separate structure called a table that does that. The idea of the table is that it stores anything that's a reference that is not like raw data, like raw bytes. And so currently that's only used for functions. You can basically, there's an instruction called call indirect that will take an index and then index into that table and then call that function. And it's type safe, so you have to provide the type signature as well. In the future, actually very, very soon, we're gonna have features where you can take any number of tables and you can store other data in them as well as opaque handles. So that way you could actually take a JavaScript object, store it in a table, and then reference it from WebAssembly. So, so tables are sort of our mechanism for dealing with object-like data. Object meaning like JavaScript object or like host object. Yeah, thank you. Question?
All right. Hi. So it was a little bit painful watching your talk, not because of your talk, but because you went through a lot of the things that we went through. So we had this project called Browsix that does basically everything that your thing does, but it also has more. So you can do synchronous I/O. You can do synchronous I/O from a file system that's mounted over HTTP. Right, it's quite general. We just ported it forwards to WASM recently. So if people are interested in using something that may make this job a little easier, it supports almost all of POSIX. And it actually supports multiple processes, IPC, all kinds of stuff.
Yeah. So basically just saying Browsix is something that does something very similar. I'm sorry I didn't mention it. Actually, I knew about Browsix. It's a very, very cool tool to do that sort of stuff. Again, yeah, running that all on the web. Yeah, thank you.
Does your project run on Firefox?
It does run on Firefox. I tested it on Firefox. There was one issue that I ran into, which is that the canvas feature that I use actually relies on off-screen canvas, which is supported in Firefox, but it's behind a flag currently. So if you try and load that up in Firefox, it currently, I think, will print an error message. But as soon as off-screen canvas is supported, then it should work. All that stuff, I tried it.
Thank you.
Yeah.
Hello. I actually have two questions, if that's okay. The first one is, why is WebAssembly advertised as 32-bit targets, and are there plans in creating a 64-bit version of the WebAssembly?
Yeah, so the question is, why is WebAssembly 32-bit? Yeah, it's a good question. I think originally it was because we figured that was all we would need for to get a lot of the work that we needed to get done. We always had plans for WASM 64, but as of now, that's currently vaporware. I think if you look at LVM, there is a WASM 64 target that could work, maybe. I don't think there are any implementations. The way that you could extend WASM 32 to WASM 64, like in our heads, we've sort of gone like, well, it should just work, right? But yeah, it's not clear. It would be a different binary format as well. So there are definitely some issues there. Yes.
Okay, thank you. And the second question is, how is actually WASI different from the mscripton? Because on your slides, you have shown how you re-implemented most of the POSIX functions, which are already implemented in mscripton. So I'm curious to know why you didn't use that and what's actually the benefit of using the WASI directly.
Yeah, okay, so the question is, why didn't I use the mscripton versions? I mean, part of it was just because I wanted to talk about you know, how this is implemented. If I just use mscripton, I'd have to sort of say, well, mscripton does this, and I don't really understand that code. But also because, yeah, I don't know. Yeah, mostly that's the reason.
Okay, thank you very much.
Yeah, thank you.
Hi. You mentioned that the WebAssembly is typed, so you push an int 32 to the stack and everything. When you compile C++ code, do the types on C++ get translated into a type from WebAssembly, or are those just the native types?
Yeah, so the question is, WebAssembly is typed, do C++ types get converted into WebAssembly types? Is that right?
Yes.
Yeah, so the answer is that it does in a sense. It's very similar to the way that LVM will lower to LVMIR, except for it's even lower than that because I think LVMIR has pointer types and things like that. And in WebAssembly, pointers are just 32-bit integers. So it really is just an index into linear memory, into the untrusted memory space. So the types are all basically lost at that point. By the time you compile it to WebAssembly, the higher types of C++ are lost, and they're converted into the lower types of WebAssembly, which currently just is int32, int64, float32, float64, and that's it.
Oh, okay.
Yeah. Thank
Hear
you.
me?
Since WebAssembly has some protection against array out of bounds accesses and things like that, what happens if you do that in your C++ code?
Yeah, okay, so the question is, what happens if you try and access out of bounds in C++ code? So the first thing I should mention is, accessing out of bounds, if you have an array and you access that out of bounds, that probably will work, right? Because we just have a big bag of bytes, right? And if you have an array that starts here and ends here, and you access outside, you're just gonna access some other data, just like you would in C++. Now, if you access something that's completely outside of memory, what'll happen is a trap. And trap is sort of like the equivalent of, yeah, like a seg fault or something, except for you can catch it in JavaScript and then do something with it. So there are a number of different traps dividing by 0. If you try and do a call indirect and the type signature doesn't match, that's actually a runtime check. So that's a trap as well. There's other traps as well. So thank you.
The question is, do you have any way to debug code, C++ code, compile to WebAssembly in a classic way as using GDB or DB?
Yeah, so the question is, how do you debug the code? And the answer is, right now, very carefully, and in the future, actually, I think very soon, there is a debugging subgroup of the WebAssembly group that is focused on this topic. I think the idea will be that you will have a separate module that has a, oh, everything went off, okay. You'll have a separate module that basically is intermediary between the WebAssembly environment and your executable, and that will be able to handle debugging for you. So it will do something very similar to like, I think in the browser, if you're running like on, what's that tool, the JetBrains browse debugger. Anyway, when you're using that, it communicates with the Chrome dev tools to be able to do debugging. It'll be something very similar to that, but it'll be its own executable that's running and doing the communication. That's the current plan, but as of now, I don't think there's much there yet. So. Yeah, right now it's a lot of printf debugging. But we do actually, I should take a step back from that. We do have some support inside DevTools in Chrome and in Firefox that's limited, but not bad. It'll give you stack traces with actual C++ names, and but it'll show you source lines, but you can't actually inspect values as if you were C++ values. So, yeah. Thank you. Looks like one more question, and that's probably it.
So adding to that question, you mentioned that you cannot alter the executable code.
Yeah.
Usually that's how the debugger servers work, by putting a trap on that. Is there kind of a hardware way of doing that, saying, I want you to trap when you get to this point?
The question is will you be able to modify the executable code to insert like a breakpoint or something, right? Yeah, I don't think that's going to be the way it works. I think it's probably going to be something more like there's a communication protocol. And so the WebAssembly engine already knows how to do all that stuff itself, so you don't actually need to modify the executable code to do it that way. We'll probably end up using the internal breakpoint structures that are already there for JavaScript. So that's my guess.
Yeah, I was thinking more like if you could have ported version of a GDB server or LLDB server, so you could do remote remote debugging.
Well, I'd like to talk to you more about this, but the session is over. So
Okay.
thank you, everyone.
Thank you.